So for vectors just in general, there were essentially two calculations that we had with vectors. If we have a vector v and it's equal to -5 on 12, we can do two things with that. We can figure out its magnitude and we can figure out its direction. So what it means when we see that -5, 12, it means we have a vector. It's inside of quadrant 2. The horizontal component of the vector is 5 units long. The -5 just means it's going to the left. The vertical component of the vector is 12 units long. The 12 is positive, indicating that we're traveling up, which is the reason that the vector is in quadrant 2. Essentially, the magnitude of the vector is the length of the vector. We can figure out the length of the vector using Pythagorean theorem. It's the square root of x squared, the horizontal component, plus y squared. 5 squared plus 12 squared is 169, and the square root of that is 13. So this vector is 13 units long. That's its magnitude. The direction, what we said when this came up in class, was that we're going to use inverse tangent of y over x, and then sort of. Right? It's not only that we're using inverse tangent of y over x, but we are using that. What inverse tangent of y over x does is it gives us back an angle. So typically for this will be in degree mode. So just to make sure if you're going along with this with me that your calculator is in degree mode. But inverse tangent of -12/5 gives us back -67.38 degrees. Now is when the sort of business comes into play. I don't care about the -67. I don't even want the -67. What I'm going to use that number for, that angle, is to determine that the reference angle right there, the one between the terminal side of the vector and the x-axis, that angle is positive 67.38. Essentially, we're just going to drop the negative sign so that we can figure out that reference angle. What we want is the actual direction the vector is traveling. The true direction this vector is traveling is the angle in standard position. So starting from the x-axis and traveling over to the vector itself. So I'm just going to kind of copy and paste of sorts the black line we just drew, and then the blue line we've got for the reference angle. The two of those together create a 180 degree angle. Right? The black angle plus the blue angle together are 180 degrees. We're interested in knowing the black angle, but we already know that the blue one is 67.38 degrees. The black one, that's the one we want because that's actually theta. That's the angle that the vector is traveling. So theta is going to be 180 minus that 67.38, which in this case is 112.62 degrees. Questions about either of those two things? We can do more. If you want to do more, we'll go back and talk through anything else we just did if you want to do that. The questions about anything we just did there, finding the magnitude, finding the direction. Okay. I'm going to scoop that up. What we can also, that was from last week, kind of a review, or is a review of both of those topics on magnitude and direction. What we can also do with vectors is add them and subtract them and multiply them by constants. So let's say that now we've got two vectors. Vector V is negative 9, 2. And vector W is negative 8, negative 3. There's a bunch of things we can do with these vectors. We can add them together. Right? So if we want to add V to W, that essentially means we're adding negative 9, 2 plus negative 8, negative 3. But how we do that is sort of by combining like terms. That's an inappropriate use of that description on my part. But the point I'm trying to convey is that we're going to add like components. That's a better way for me to phrase that. But we'll add like components. X plus X gives us negative 17. Y plus Y gives us negative 1. So to add vector V to vector W, add the X's together, add the Y's together. We can subtract the vectors using the exact same idea. That would be negative 9, 2 minus negative 8, negative 3. And how that works is the exact same way. Negative 9 minus negative 8 this time. We're not adding, we're instead subtracting. So negative 9 minus negative 8 really means plus 8, so negative 9 plus 8 is negative 1. 2 minus negative 3, so 2 plus 3, that's 5. So we can add them, we can subtract them. We can also multiply them by constant terms. So maybe we want to figure out 3V. That means we're going to multiply 3 times the vector V, 9, negative 2. 3 times negative 9 is negative 27. 3 times 2 is 6. So in this case, we're multiplying the individual components by that number we have out in front, whichever one it is. Whatever the number is, 3 or a half or a third or 25. Questions about anything there? So what we're interested in doing with this is answering application questions. That's the topic for the week, applications of vectors. And so the general idea is that if we have multiple forces acting on an individual item, the net effect will be found by adding the vectors that represent all of those forces. So let's say we have, trying to come up with something that, let's say we have a ball. I'm not sure what kind of ball I'm envisioning, but let's say that we have a ball. Let's say that it's flying through the air. So let's say that someone threw the ball in this direction. Let's say that the wind is blowing in this direction. Let's say for some other random reason, just me making things up, that there's a fan blowing very forcefully in this direction. Right, so we've essentially got 3 vectors acting or applying their forces onto this little blue ball there. So if we have, ultimately the questions we're going to be answering are these 2 that I'm writing. So ultimately, we're interested in answering the questions of which direction will the ball ultimately end up going, right? So we've got these three forces, the person who threw it, the wind that's blowing, and then this fan that I kind of strangely threw into this scenario. The ball's going to go somewhere, but where it ultimately ends up is going to be determined by the forces acting on it, right? So maybe a balloon would be a better example because we can really easily impact the direction that a balloon goes because they're so light. So if you throw a balloon up, if you're standing in a room where and maybe have a fan on above you, if you throw a balloon up in the air and the fan is blowing and you decide that you're going to try to blow on the balloon too, you've got three forces acting on the balloon. All three of them dictate to some degree which way the balloon will travel and how quickly it's going to be going. What we can do to make that whole process a lot easier to work with and these calculations a lot easier to make is to figure out the vectors associated with each of those forces and then just add them together. Right? So maybe we have 4 or 5 or 6 different forces acting on an object. Well, we'll get 4 or 5 or 6 different vectors, however many, that correspond to the number of forces at work. But then if we just add those together, we'll get a single resulting vector. So we'll ultimately have a single vector once we add them all together. And that one vector will be the one we work with. We'll use that single vector to find the direction. We'll use that single vector to find the magnitude or speed that the object is traveling. So that's where we want to go. That's going to be the topic for the week during class. But that's the foresight, or that's the future. That's my glimpse into the future of what's ultimately going to happen. So our task, what we're going to do today towards that purpose, is look at some application problems and work with at least figuring out the vectors at work. So I put a screenshot of a question into our chat. We'll read it out loud and actually we'll work on a picture for it together. But what's happening here? It says Rebecca leaves her house. So we'll have her house here. So let's just use a point. Here's Rebecca's house. She leaves the house and walks 3 miles northwest. Once she gets there, she turns and walks 2 miles east. After that, she turns again and walks 5 miles southwest. So at the end of all of this, Rebecca ends up somewhere else. I'm going to go back to the black dot now. But Rebecca leaves her house and walks these directions for these distances and ultimately ends up somewhere else. What we can figure out is, so the question is, how far is she from home? That's just what that's asking us is to figure out this distance right there, the one that I've, the little black dotted line that I drew, dashed line. So one option we have is that we could create a series of triangles and find missing side lengths and angle measures. We could go about it that way. That's totally fine. Likely what's a simpler process is to find 3 vectors, one for each of these movements, and add them together to get Rebecca's net displacement from her house and just work with that vector. So what we need to do, though, we need to take each of these 3 vectors and write them in component form. That was a topic from last week. So we'll look at each one of these. I'm going to actually drag each of these vectors separately over here off to the side, and we'll look at them on their own. So the first one was 3 miles northwest. So just just picturing the little red vector there, 3 miles northwest. Northwest means exactly in the middle of north and west. So exactly in the middle there means that this angle is 45 degrees, the reference angle. Remember, additionally, one of the topics from last week was that if we want to take a vector, if we know its magnitude and its direction, I'll write this up here in black as a refresher. If we know the magnitude of a vector and its direction, then we can write that vector in component form by multiplying the magnitude by cosine of the direction and the magnitude times sine of the direction. That'll give us the horizontal and vertical components. That's exactly what we're going to be using here. Our task again, ultimately we want to add all three of these vectors together, the red one, the blue one, and the pink one, but we have to have them in component form first. So, to use that idea, I'm just going to label this as vector A for the first movement, and then we'll have a B and a C after that. The magnitude of that vector is 3, right? The magnitude is its length. We were already originally told that that Rebecca travels 3 miles. So we're going to multiply 3 times cosine of an angle and 3 times sine of an angle. But what is the angle we need? It's not 45 degrees. What's the actual angle in standard position associated with that vector? Just like before when we did it, we had, I think, 180 minus 63 or something like that. 180 minus 67. To find the actual angle, the angle in standard position associated with this vector, we would use 180 minus 45 to get 135. So the actual direction in standard position associated with this vector is 135 degrees. And then we repeat for each of the other 2 vectors. Questions, though, about anything we did for that first one, the one that I'm calling A? Cool. So what about this next one then, vector B, the one that I've labeled as blue in the diagram? We'll work with it over here in blue. That one, it's going to be a little hard to draw it because it's on the x-axis, but that one is 2 miles directly east. What angle is associated with that vector? What angle?
0?
0, exactly, it's 0. So to write this vector in component form, exact same idea, 2 cosine 0, comma 2 sine 0. I'm going to do the pink one over here just so that we can have all of them on the same screen. The last one, southwest for 5 miles. Whoops, I don't know what that happened. What we know, again, anytime you see northwest, northeast, southwest, southeast, that always means exactly 45 degrees in whatever quadrant that vector is in. So we know that the reference angle here is 45 degrees. As always, what we want is the angle in standard position. In this case, the angle in standard position is 180 degrees plus 45. Right? 180 gets us to here. 45 gets us the rest of the way to the vector. So 180 plus 45, the angle there is 225 degrees. So our vector in this case is going to be 5 cosine 225 and 5 sine 225. So this is what we'll call vector C. So these are our three vectors. What we're actually going to do is get some decimal values for them so that we can add them a little more easily. But we at least now have each of these vectors in component form. Questions about how we got there? Just drawing on similar stuff to what we did last week. Last week it was probably just a single vector. This week we'll have multiple of them. So just repeating the process a couple of times if necessary. All right. So ultimately what we want to do is have a vector for A, a vector for B, and a vector for C. So A, what I'm going to do in my calculator, since we can use them now, is do 3 cosine 135 and 3 sine 135. For B, we'll do 2 cosine 0 and 2 sine 0. And then for C, we'll do 5 cosine 225 and 3 sine 225. Or sorry, 5 sine, sorry, not 3, 5 sine 225. So we took this question, we drew a diagram that incorporated the movements for Rebecca, used those to help figure out angles, the angles for each of these movements, and then got vectors for them. What our task is, what we're doing this for, is to add them together to get a single net or resulting vector for all of Rebecca's movements. So if we add all of these together, A plus B plus C, what we're going to get is a net vector. So negative 2.12 plus 2 plus negative 3.54. The horizontal component for Rebecca's displacement from her house is negative 3.66. Adding the y's, 2.12 plus 0 plus negative 3.54. We get negative 1.42. And what this tells us is that from where Rebecca originally started at her house, ultimately, she is 3.66 miles to the left. Let me get a different color. This we can use green. She is 3.66 miles to the left, 1.42 miles down. So she is here with respect to her house. So I'm going to turn that into a vector since that's actually what we're looking at. But that's what this net vector or resulting vector tells us. Is overall, if we incorporate all of these motions, all of these movements, all of these distances, where does Rebecca appear relative to her house? And so the question of how far is she from home is asking us for the magnitude of that vector, right? How far is she from her home? That's the distance of the black vector right here, the length of it. To find the length of it, or magnitude, they're synonyms, the magnitude of the net vector is the square root of negative 3.66 squared plus negative 1.42 squared. Again, this is finding the magnitude is a topic from last week too, so we can chat about that this week as well. So ultimately, Rebecca is 3.93 miles from home. Questions about anything that we did there? Anything to go back and talk about more? Anything that makes sense or? So if not, I put our next question in the chat. It's really similar. There's two vectors for this one. The one we just did obviously had three. There's two vectors that work for this new example. So what I'm going to do is give you a moment to construct a diagram and see if you can write the vectors, the two vectors that work here, see if you can write each of them in component form. Well, obviously, of course, we're going to talk about it in a minute. I'll give you a chance to try it first.
Are we writing we have them as cosine and sine?
Eventually, we want to have them in decimal form. So if you can start with sine and cosine, or you can, if you have the angles and already know them, you can feel free to just punch it in the calculator from the beginning if you want to do that. All right, so let's see how it went. For every word problem, it's likely that for every word problem you'll ever see me answer, I will begin with a diagram. I think diagrams are exceptionally valuable ways to begin word problems. So what's happening with this one is that John, so this little point is going to be John. Picture him, he's standing on a cruise ship. That'll, that little rectangle is, us looking down onto the deck of the cruise ship. John's walking west on a cruise ship. Anytime you see due west, that means exactly west or directly west. So he's on the cruise ship and he's walking this way. The speed he's doing that is 1.9 miles per hour. But in addition to that, I didn't mean to do that in black, so I'm going to draw the exact same thing just in a different color. In addition to that, the ship itself is moving. The ship is traveling directly north at 12 miles per hour. Our question, so, picture John sitting, standing on this boat in the middle of the ocean. He's walking this way while the boat's moving that way. So ultimately, what if we were kind of in the water looking up at just John, if we could take away the boat and literally only just see John walking sort of on the surface of the water, we would watch him, we would see him, and he would be walking in this direction, right? The boat's pulling him north, he's walking west, so ultimately he ends up traveling somewhere between north and west. That's the net effect of his movement. But probably more towards the north than towards the west, because that number is a lot bigger. But what we're after, right? This is what I'm focusing on now is the portion of the question that says relative to the water. So if you're talking about how fast is John walking, John is only walking 1.9 miles per hour. Your question is how fast is the boat moving? The boat is moving at 12 miles per hour. But John, if we were to stand in the water and literally be still and to watch John himself walking, we would see him walking between north and west at a different speed than either of these two, right? He's going to be walking at a combination of the two. Not necessarily 12 plus 1.9, but some combination of them. So our task first is to write a vector for each of these. To do that, we need the angles for each of them. So the blue vector, we'll call it A again. Let's call it, A is fine. What angle, so picture the unit circle laying on top of this, what angle is that vector at, the 12? What angle? 90, yeah. So 12 cosine 90, I'm going to scoot this pretty far over. 12 cosine 90 and 12 sine 90. What about the red vector? We'll call it B. What's the angle there?
180.
180. So 1.9 cosine 180. 1.9 sine 180. And ultimately what we get for A is 0.12. And for B, we get negative 1.90. So that the net effect, the net vector or resulting vector for John is found by adding the two of these together. Negative 1.9 plus 0 is negative 1.9. 12 plus 0 is 12. So this is the net effect that we would witness if we were to be, could remove the boat and just see John kind of walking on the water, but walking 1.9 miles per hour east while being forced 12 miles per hour, 1.9 miles per hour west while being forced 12 miles per hour north by virtue of being on this boat. So our questions so here's the vector, just to point that out. The resulting vector, the net effect, is negative 1.9 with 12. Don't necessarily mean for that to be in red though. And so the speed John is walking, speed always means the speed and the magnitude are the same thing. So to get the speed, aka magnitude, the magnitude of the net vector, it's going to be the square root of x squared plus y squared. In this case, that's 12.15 miles per hour. So just a little bit faster than the boat is actually traveling. But then we get the direction business. So that's, always keep in mind that the sort of part there. So inverse tangent of y over x we get negative 81.00 actually. So just we'll round it to negative 81 degrees. What does that mean? Where should I label 81? Again, I'm going to ignore the negative sign because we don't so much care about that. The negative sign is relevant. It's not a problem, but we're always doing this sort of that we mention in class all the time. But the negative 81, or actually the 81, is always the reference angle.
So the direction is always the reference angle?
No. When we use the inverse tangent function, what we're after is a reference angle. The direction is going to be the angle over here in standard position. Just like the earlier one we did, or maybe, yeah, when we had the 67 degrees, we always want the angle in standard position, but we need the reference angle so that we can get the angle in standard position, the black one. Because to give the actual direction, it's going to be 180 minus 81, which is 99 degrees. So John, I think that was his name, John is walking at a direction of 99 degrees, going 12.15 miles per hour, all relative to the water. Questions about anything there? Okay. So one more of these, and then we'll kind of switch gears and talk a little bit about equations. We'll review some factoring approaches and talk about identities a little bit. Like this, like the one we just did. I'll give you just a minute to have a shot at creating a diagram and finding these vectors. There's two vectors here again, one for the plane, one for the wind. Remember what south 31 degrees east means. That means from the south, turn that's west. From the south, turn 31 degrees towards the east. So the vector is there. 31 degrees is where I've got it labeled here. It's not the reference angle. It's the angle, in this case, between the y-axis and the vector. One more thing I'll point out because we haven't encountered this yet. When the wind is blowing from the southwest, what that means is that it's actually blowing in the direction of northeast. And so if you think about standing outside, if the wind is blowing from the south, imagine me, I'm facing you in the monitor and the camera. Let's envision me facing north. If the wind is blowing from the north, that means it's blowing in my face towards the south. If the wind is blowing from the south, that means it would be blowing at my back and towards my computer sitting there. So from the southwest means the wind is actually blowing in the direction northeast. Okay, so I'll give you some time to have a shot at each of those vectors and We'll see how it goes. So we have these two vectors. Let's do the wind first. That one will be a little maybe easier, I don't know. But so from the southwest means towards the northeast. We know that anytime we're talking about exactly northeast or exactly southwest or any of those, that the reference angle to use is 45 degrees. Since the vector for the wind is located in quadrant 1, the reference angle there, 45, that actually is also the angle in standard position. So the vector for the wind, it's going at 14 miles per hour. So the vector is going to be 14 cosine 45. Comma 14 sine 45. The vector for the plane, for the actual speed of the plane, is going at 500 miles per hour. I'm going to write that down here so the picture doesn't get too cluttered. I didn't draw a very large picture. But what we need is the reference angle here. We need the angle between the vector and the x-axis. Since the bottom angle, the black one there, is 31 degrees, that tells us that the reference angle is 59 degrees. So the vector for the plane is 500. Oh, sorry, we're not ready yet. We need to get, sorry, what we actually need, I got the reference angle, we don't quite so much need that. We need the angle in standard position. So we need this red angle that I just drew in standard position, so from the x-axis all the way around. So to get that, we'll use 360 minus 59, which tells us that that angle is 301 degrees. So the plane's vector then is 500 cosine 301, comma 500 sine 301. We can get approximate values for these. We can get decimal values. So 145 cosine 45 is 10. Oh, sorry, not 145. 14 cosine 45 is 9.90. 14 sine 45 is also 9.90. The plane is 500 cosine 301. Sine 301. And then the net vector, we'll add those together. 257.52 plus 9.9. 9.9 minus 428.58 is negative 418.68. So that's the net vector. Ultimately, where the plane ends up traveling can be determined using the net vector that we just got. So when we're after the true speed and the true direction, this is a vector to be using, not the one for the wind, not the one for the plane, but the one that incorporates the two of them together. So when we're after the magnitude or the speed, that's what speed means, it means magnitude. It's the square root of x squared plus y squared the plane's traveling approximately 496.8 miles per hour. The direction will start with inverse tangent of y over x. That's negative 57.43. But remember, what that's telling us is that the vector we've got, the net vector, that the reference angle there is 57.43 degrees. What we need is the actual angle in standard position. So that's going to be 360 minus 57.43. So the actual direction the plane is traveling is 302.57 degrees. Because the wind is blowing from the southwest. I'm trying to find the question. The wind is blowing from the southwest. I'm going to scoot it up. And so southwest is here, but it's not blowing towards the southwest, it's blowing from the southwest. So the wind starts from the southwest and blows in the direction northeast.
Oh, I missed that last part. Okay.
So if the wind was blowing from the north, what it would actually be doing, though, is blowing towards the south. Other questions about anything with these? And normally we don't work through the entire question. We actually answered all three of these questions, just because the things were being asked, magnitude and direction were topics from last week, so we can. It falls under a prereq skill at the moment. But actually constructing the diagrams, that's the biggest focus. That's the new thing for the week, being able to create the diagrams and find the angles for the vectors, and then of course adding them together. So what we'll do for our last little bit of time is the last half hour is talk about factoring things. So we don't need the whole half hour for this, but let's say that we need to factor something like this: 2 sine squared x plus sine x minus 1. An option from a few weeks ago, when we talked about factoring, this will be probably the third, maybe even fourth time we've looked at it. But an option we had for factoring is to use what's called substitution. So maybe, if when you see this and you see all the signs in here and that makes it a little tricky, you can make a substitution. We can say, we'll use a substitution, u equals sine x. And so we can rewrite this as 2u squared plus u minus 1. And then we can factor this. Anytime the leading coefficient is not 1, we can use what's called the AC method. A, B, and C refer to the coefficients, or A and B are the coefficients for their term, C is the constant term. But how the AC method works is we're going to multiply A times C to get -2. What we do with -2 is look for factors of -2 that add to +1, that middle term. The two numbers that do that are +2 with -1. And so we then separate that middle term into +2u and -1u. The 2u squared in front is the same, the -1 at the end is the same. We're just separating that middle term. And then we can factor this, now that there's 4 terms, by grouping. From that first group, we can take out a common factor of 2u. From the pink group, we have a common factor of -1. And so ultimately, this factors into 2u minus 1. The outsides go together, and then the insides get copied just a single time. But we don't want to have these u's in the work. What we need are signs. That's the original question, the one in black that we haven't actually spent much time specifically working on. So bringing that back down here, we can undo our substitution now. It's going to be, instead of u, we're going to write a sine x. So this really factors into 2 sine x minus 1 times sine x plus 1. That allows us to set each of those factors equal to 0 and solve for x. So that says that sine x is 1/2 or sine x is 1. Sine is 1/2 at pi/6 and 5 pi/6. Sine is 1 at 0. Those are in radians. So again, we can actually solve this from beginning to end as well, because it's still involving prereq things. This is just a review of factoring, because that will come up again this week as we use identities inside of these equations. So you don't have to use the AC method. I've not, hopefully said that every time we've looked at it. It's just an option you have for factoring if the leading coefficient is not 1. So let's, questions on anything from there? Mostly from the factoring part, that's the biggest focus that we've got. But I guess questions about anything would be fine too. So that's just a review of the AC method to have it in the recording. We've talked about it, like I said, I think 3 or 4 other times. It's probably in all those, I mean, it would be in all those recordings, but just to have it in this one so that it's easy to come back and look at again if you want to do that is a big point of why it's here. But the focus for this week, the new focus, this will be part of the work, but a new focus is solving equations with identities. So that's going to allow us to solve equations that look like this. When we're solving equations, what we would like is to have, if possible, to have all of the same trig functions in the equation. So only sines or only cosines or only tangents. It doesn't make a difference which of those. It would be really great if they could all be the same. Currently, with this equation, they're not all the same. But what we can do is use an identity to help. We have an identity that says, hey, you can replace sine squared x with 1 minus cosine squared x. That's the very first identity off of page 92. Sine squared x plus cosine squared x equals 1. That means that sine squared x is 1 minus cosine squared x. So what we will do is actually make that replacement. In place of sine squared x, we'll put 1 minus cosine squared x. Keep everything else exactly the same. There's more work to do, right? We're not finished, of course. We need to solve for x. But we at least now have an equation that involves only cosines. That's one of our desirable situations. And we have that. We've created that. We use an identity to help us in that process. What we will do next is distribute the 2. We have some like terms we can combine. And then again, we're at a point where we would like to factor this. It's really not ideal to factor if the leading coefficient is negative. So what I'm going to do next is to multiply the entire equation by -1 to get rid of that. But cool, now we're there. We could, if you want to make a substitution, we did that in the last one. That's another tool that you have at your disposal. You can make a substitution there. So we can use the substitution, let u equal cosine x, and we can rewrite this as 2u squared minus 3u plus 1. The AC method is, again, a tool that we have for factoring when the leading coefficient is not 1. A times C, that's 2. Factors of 2 that multiply to -3, those would be -2 and -1. So we can separate that middle term into -2u minus u. So that now that we have 4, we can factor by grouping. First group has a common factor of 2u. The second group has a common factor of -1. So that ultimately that blue piece factors into 2u minus 1 times u minus 1, which tells us what we really need is 2 cosine x minus 1 times cosine x minus 1. So we're not finished solving it. I'm zooming out a little bit to have all of the identity work and then the factoring work on the same screen for just a second. Questions about anything we said or did? So the new part is up here when we're using the identity. After that, factoring and solving, that could have been something we did a couple weeks ago and was something we did a couple weeks ago. But the new part is using these identities to help us solve equations using earlier skills too, though. Okay, so I'll zoom back in down here on the bottom to wrap it up. Setting each of these equal to 0, we would get 2 cosine x minus 1 is 0. Cosine x minus 1 is 0. That tells us that cosine x is a half, which occurs at pi over 3 and 5 pi over 3. Cosine x is 1. That occurs when x is 0. So again, for test 3, you'll have the identity sheet. You can, the same one you had on test 2, you'll have that to work with while you're testing. You don't need to memorize anything new that you didn't already need. You don't need to memorize any new identities that you didn't already need to have memorized for test 2, but we will spend more time in unit 3 working with them. So I'll scoot that one up and jot down one more. So let's say we have something like this, 4 cosine, let's do 4 sine x plus sine 2x is equal to 0. What we would like is to have all of the same trig functions in the equation, which we do have here, they're all sines. In addition to that, we need the insides of the functions to match as well. Currently, our insides here don't match. We need an identity. There is an identity that can help us. Any thoughts on what identity we might use? Michael typing something. Yeah, there, right, for sure. The double angle rule for sine 2x says that we can replace sine 2x with 2 sine x cosine x. So that's exactly what we're going to do. We get 4 sine x plus 2 sine x cosine x is 0. So now we've kind of created another problem, sort of. It's actually not a problem. We'd like to have the same trig function if possible. Every time I've mentioned that, I have thrown in that little caveat if possible. We would really like to have the insides of the trig functions match. if that's possible too. So we can make the insides match. Now all the insides have just x. But now we've introduced this another function in here. We don't just have sines, we also have cosines. But since we only have two terms, the 4 sine x and then the 2 sine x cosine x, since we only have two terms, it's really not that big of a deal that we have the cosine function, because what our next step is going to be is to factor out the common factor from each of these two terms. The common factor is 2 sine x. When we factor that out, we're left with 2 plus cosine x. So cool. We factored it. To solve it, the factors need to have a single trig function, which they do. We'll set the first factor equal to 0, the second factor equal to 0, and solve for x. This first one, if we divide both sides by 2, we get the sine x equals 0. That happens when x is pi over 2, or, oh, that's not true. When x is 0, or pi. For the second one, if we subtract 2, we get cosine x equals -2. But we can't solve for that. Cosine values are only ever between -1 and 1. So -2 is not a possibility. So the only solutions here are 0 and pi. Questions there? And in addition to that, questions about anything. So we've got, that's the end of what's planned. We've got time for any questions you've got. I know there was a test last week, so not a whole lot's going on. But if you have questions about anything, we will talk about the questions about this or questions about anything else. I did put the new link in the new survey in the chat. That's the post survey. Same questions, different. It's stored in a different questionnaire, different survey though. So if you could complete that before you leave, that would be really cool. But we'll spend the rest of our time answering any questions you've got from today or any other day.
Can you possibly go over the one I put in the chat?
Yeah. So poll. Okay. So I'm going to copy that diagram. I'm going to exaggerate it a little bit just so I can have a little bit more room to draw in here. So this red line is going to be the pole. We've got 8 degrees here, 59 degrees down here, 46 feet here. So we need to figure out how tall the pole is. That's the distance in the picture from B to C. I'll highlight it here in blue, but we need to figure out this blue distance. What we can do, just using the information that's already present, we can figure out this purple angle. Let me take this away so I can see. We can figure out that purple angle. How can we get it? Any ideas?
Would it be 90 degrees?
No, not 90. The two of these together would be 90. But
180?
No. The two of them together, the red one plus the pink one, they make 90 together. Since the red one's 8, that leaves 82 degrees left over for the pink one. 90 minus 8. Now that we know the 82, we can also get this third angle, the one up here at the top, by subtracting 180 minus 59 minus 82 to get 39 degrees. But to get the length of the pole there, we can use the law of sines. So we can do sine 39 over 46 equals the sine of 59 times x, the length of the pole there. We cross multiply, we get x sine 39 equals 46 sine 59, which means x is 46 sine 59 over sine 39. Michael, I don't have any. I have the three that I can make something up, I guess. I don't know. What are you after for it? Like just drawing and just labeling them or what? So let's say that we have a boat. Let's say that we have a boat traveling 16 miles per hour northwest, and we have the current flowing 4 miles per hour east. So that's the scenario. What I'd like to know is what's the true speed and the true direction. So I'll give you a second to work through that if you want to. If you just want to work on it together from beginning to end, we can do that too. Do you want to work on it for a second on your own, or you just want to go through it? Yeah, okay, that's fine. So the boat's traveling 16 miles per hour northwest. The current's flowing exactly east at 4 miles per hour. I know those the lengths of those are pretty exaggerated, but just to have enough room to draw everything. So the vector for the what?
Why is it in the first quadrant? I thought it would be in the second. Oh wait, never mind.
So the boat's actually traveling northwest for this one. I don't know if you're asking this because of the wind question from earlier. But in that one, the wind was blowing from the southwest, and that meant it must be blowing in the direction northeast. Oh no! Sorry. Okay, I see your question. Yeah, because I just reread what I wrote. Northwest is in the second quadrant. You're right about that. Sorry. I need to move that around then. So northwest, yeah, you're totally right about that. 16 miles per hour northwest, 4 miles per hour east. So what we know, we can actually go ahead and write the vector for the current. It's 4, 0. Right, cosine at 0 is 1, sine at 0 is 0. The vector for the boat itself, we know that the reference angle is 45, and 180 minus 45 is 135. So the vector for the boat is 16 cosine 135, 16 sine 135. And that gives us negative 11.31 with positive 11.31. And so the net vector, or the true vector, that's another way that you could see that. The true vector is found by adding those together. That gives us negative 7.31 with 11.31. And what we want to do with this, we want to find the speed and the direction. The speed is going to be the magnitude. That's the square root of x squared plus y squared. .47 miles per hour. The direction, first we'll start off with inverse tangent of y over x. Negative 57.12. Really, don't so much care about the negative part, but I need to know the 57. We need to know the 57 so that we can actually get the real angle there by using 180 minus 57.12. So the real angle, the one in red, is 122.88 degrees.
I had a question. For the law of sine and the law of cosine, does it matter how you label the triangles?
Yeah. What do you mean though?
Like for the sides, like I know for, well, I just noticed this. I didn't know if that was how it was. Like for like the law of sine, it would be A, B, and C, and then for cosine, is it C? Oh, are they always like that?
It doesn't make a difference.
Mhm.
So everyone we've ever done in class, I've always labeled exactly like this. If angle A is always across from side A, angle B is always across from side B, angle C is always across from side C. That always has to be the case. But it doesn't matter if you start with A or B. You could label it A, B, C like this. It would just be side A is down here, side B is on the left, and then side C is on the right.
Okay.
So that side A is still across from angle A. Side B is still across from angle B. Side C is still across from angle C. Like that, the sides always have to be paired with their angles in that manner, but it doesn't make a difference where you start with A or whether you start with B.
Okay.
So we'll do the one that you put in the chat.
Because I don't know if I labeled them wrong or why I couldn't get the answer. Because I feel like I had another one like that and I got it right.
So two streets meet at a 79-degree angle, and a park is being built in the shape of a triangle. So this will be our little park. Find the area of the park if along one road the park is 170 feet, and if along the other it's 225 feet. So this we can use the area formula. We know two sides and the angle between them, so we can use 1/2 of the sides multiplied by sine of the angle. So 0.5 times 170 times 225 times sine 79 is, so yours is close. It wants us to round to the nearest whole number, so 774. Did you use this formula or did you use some other approach?
No, I did something completely different.
What did you use, Heron's formula?
The
square root?
No, I just had like
Yours is close.
I think I did C squared equals A squared plus B squared minus 2.
Oh, okay, that's fine.
Does that give you the same thing? Because
Well,
that's
no. So what you would have been finding using that equation is this missing side over here. My hands off. You would have that would have told you this side. I'm not sure how that.
I don't know how I got that number.
I mean, if maybe once you got that side, you used Heron's formula, that could be.
Maybe. Okay, but I see what I did wrong now.
I don't know, but if you know two sides and the angle between them, if you just need the area, that equation 1/2 AB sine C is really, that one's pretty quick just because you don't need to find any missing information. You already have everything you need. All right, it's 4:31, so we need to depart. I'm going to stop the recording.